Okay, off we go. So picking up where we left off last time, we were talking about change of variables. And let's see, let me scroll back real quick. We saw, for example, our most recent example, the case where you're interested in an integral over this domain, right? This being this tilted square like this. And of course, this would be a pretty inconvenient integral to compute the old-fashioned way. Just, regular old, dx, dy, or dy, dx slicing would turn this into three separate iterated integrals. That's not a good plan, right? So what we found in our general idea of change of variables is that if you can view that as being an image, specifically an image of a, presumably, hopefully, more desirable domain, then you can do this thing called a pullback, right? And the idea of a pullback is that instead of dealing with an integral on this domain, we relate that to an integral of the same value defined on our more desirable domain. Okay, so that's the big picture. We went through the details of this example last time. As I commented last time, I wanted to, let's get some wins in the win column before we start getting into details. And so here's a couple of those details that, now that we have been successful a couple times, let's go ahead and recognize. It is important that the change of variables function be continuously differentiable. That's just the harsh reality of little technicalities that aren't what this course is about. But it is important that be the case. Now, good news, most of the change of variables functions you're going to have a temptation to work are continuously differentiable, and there's no problem. So by and large, this doesn't really affect day to day very much. It also has to be invertible, and this is a more subtle point. It's less immediately clear why we would need to care about this. It turns out to matter really importantly. And if we had just loads and loads of extra time, I would love to talk about that as to exactly why that's important. But again, we don't have those loads and loads of time. So I'm just going to have to leave that as it is. But anyway, make sure whatever you do, make sure you can undo. And of course, this example here, our change of variables function was a rotation. Is that invertible? Well, yes, because you can just rotate back. Right, so clearly invertible. Okay. So let's actually play with that idea of the inverse transformation, and I'm going to make a couple of observations. Nothing really particularly deep at first, but we know that when x and y are your outputs and u and v are your inputs, we know I've already asserted anyway, I've claimed, that you take the partials of the outputs with respect to the inputs and compute according to that formula, and that gives you your stretching factor. Okay. And that's the general, the general form is that you're looking at the partials of the outputs with respect to the inputs. Okay. Now that said, let's suppose we were to look at the inverse function, in other words, going the other way. Now, instead of thinking of x and y as functions of u and v, we're going to think of u and v as functions of x and y. Let's just say, right? Well, our stretching factor formula is still the partials of the outputs. The outputs are now u and v. Right? With respect to the inputs. Okay, well, yeah, but the inputs are now x and y. So really, it's not even a different argument. It's morally the same argument. Partials of the outputs with respect to the inputs. I guess one could quibble that, I drew my little diagram kind of backwards. We tend to like to write things left to right, and this is right to left. But whatever, that's just documentation, right? The idea is really the same. Okay, now with that noted, let's entertain a third option. The third option is, imagine you have little pieces of area over here, as we always do. And let's imagine what happens when you push that forward and then immediately push it back. And what happens to a little piece of area in a situation like this? So, well, I hope it's clear that if, in fact, pushing it back is the inverse, then, in fact, you get exactly that same area. That little orange area is its own image by the over and then back again, by which, of course, nothing happens, right? So, altogether, that has an obvious stretching factor of 1 because nothing happened, right? So the big idea then is that, let's see your color choices. We've already agreed that stretching factor that's the part that happens first, and that stretching factor is this. And then we've already agreed that coming back, well, we know that stretching factor is this. And of course, doing the purple option is just sequentially doing the green followed by the dark blue. And so, in fact, that product, being as it is sort of the elements of that combined composition that has a factor of 1, the product of those factors has to be 1. Okay, or said differently, those factors are reciprocals of each other. So, nice little argument and nice little conclusion. Let's take a moment to recognize how satisfying this is, at least from a notational standpoint. It makes it look like I've drawn the conclusion that the reciprocal of a fraction, whether you just flip the numerator and the denominator, and okay, well, sure, of course, why is this at all interesting? Because, remember, those aren't fractions. They're determinants. This is not an obvious statement about determinants. In fact, it's not even clear that the matrices that we're looking at, the determinants of, are immediately related to each other. Right? That's another whole question. Right? So the fact that these determinants behave like fractions is not obvious, but it is satisfying. Right? So this makes us it makes me anyway like this notation of writing these stretching factors as fractions, because in this way as well, in addition to what we saw last time about how they kind of behave like fractions, this is another example of how these things behave like fractions. And this is going to end up being really useful in the next example. Okay, so here we go. This next example is a little bit of a weird one. It looks highly manufactured. I'm going to start by pointing out that it isn't. These 4 curves right here, I'm going to let y'all spend some appropriate time thinking about what these curves look like. It's it's an algebra thing, it's a high school algebra. So 2 of those curves you probably recognize as being hyperbolas. The other 2 you can kind of relate to those first 2 by, well, it's going to be a little bit more this way, a little bit less that way. Anyway, good exercise to think those through. Persuade yourself this is what these 4 curves look like. And we're interested in the region that's bounded by those 4 curves, and that's this region here that I'm shading currently in orange, and which, to keep my picture from getting muddled, I'll just, display like this. It's the shaded region R there. Okay, so that looks weird, it looks arbitrary and manufactured, made up, and when in the world would this ever come up naturally? And let me tell you, it actually comes up very naturally. Correction, something that is very, very similar to this comes up very naturally in thermodynamics. Right? Who'd have thunk it? Right? But someday y'all will take a thermo class, and when you do, you'll study this thing called the Carnot cycle, the Carnot engine. And it is fascinating discussion, very important to physics, therefore very important to engineering. And when you analyze the Carnot cycle, a figure that looks almost exactly like this comes up very naturally. So anyway, this is not manufactured nonsense. This is a picture of something very relevant and real that is in your futures. Okay. So with that said, let's suppose, very plausibly, that I might want to do an integral over this region. Right? How would I compute this integral? And let's take a moment to recognize that that domain stinks. right? Whichever way you slice it, you're going to hit those corners in the middle. And by the way, the bounds of the integrals are going to have some weird functions in them. Depending on what your integrand is, this could get weird, right? So this is very concerning. It is not a friendly looking integral. Okay. All right. So here's the trick. We're going to use change of variables. You probably saw that coming, of course. But here's how we're going to use change of variables. We're going to create our own change of variables function. There's a clever insight that goes into making the choice that gives us a good change of variables function. Here's the insight. It's kind of a multi-step process. The first step is to take whatever formulas you're given and make sure that you have them written as level sets. Stuff equals constant. Very important. So for example, if it comes to you as, y equals 1 over x, don't leave it like that. We can't use it in that form. Rewrite it in such a way that you have level sets. Okay, that's step 1. Step 2 is to now look at the two functions whose level sets, the two functions whose level sets give you your curves. Those two functions, make those your change of variables function. Right? The first one, call it u. The second one, call it v. If you follow this process, then really good things are going to happen. All right. Now let me point out what really good things happen here. We'll start off by looking at, for example, this curve right there, xy equals 1. Let's see, that's this curve right here. What does that curve look like over here in the UV world? And, golly, it's a little scary at a first glance. We've got a weird curve. We've got to plug into a weird function. It's actually very easy to argue this because, wait a minute, the curve is xy equals 1, but xy is u. So when I say xy equals 1, in the language of u's and v's, that translates very simply as u equals 1. And so that curve turns into a straight line, and even better, a vertical, perfectly vertical straight line. Right? Now you can see that this is an immediate consequence of the two choices that we made, right? I chose the change of variables function so that this would happen. Right? And also you can see why it's important that these be written as stuff equals constant. Because I wanted that resulting thing that I'm eventually going to call u to equal to a constant so I would get a straight line. In particular, a vertical straight line. So that's the big idea. And we see that curve, purple curve on the right, turns into the much more desirable purple curve on the left, and likewise for the others. For example, let's look at this one here, xy squared equals 4. That's this curve right here. What does that turn into? Well, if xy squared is equal to 4, that just says v equals 4, and that becomes that edge right there. Again, nice and straight and horizontal in this case, perfectly straight line. So the beautiful thing then, having chosen this change of variables functions as we did, our terrible domain there turns into our favorite domain over here, namely a rectangle. In fact, even better, I suppose, a square. But anyway, clearly much more desirable domain. How we doing? Is everybody with me? All right, so really cool trick. Be on the lookout for this. Now there are some details yet to be dealt with. Of course, I need to know the stretching factor. And let's see here. I know how to write u's and v's in terms of x's and y's. I have that right there. Let me recognize real quick. I could, in this example, I could solve for x and y. That's true. The purpose of this example, though, is not to get the answer. The purpose of this example, as is most of the time, The purpose is to understand a method, right? To understand to give you a tool for your toolbox. So let's proceed with the intended method. Let's ignore the fact that there happens to be a workaround in this case. I promise there are plenty of other cases where there is no such workaround, where you cannot solve for X and Y. Can't do it. Won't happen. Right? The problem with those examples is they're more technical and ugly, and they don't serve as well as first examples. So anyway, here we go. I know how to solve for u and v in terms of x and y, so I can compute those partials. I can take that determinant. I get that stretching factor, and I claim that's just not the stretching factor I need, right? And let me show you why we need the reciprocal. Don't forget, we started with this as our integral. This is what we need to compute. It is an integral dx dy. Don't forget, what I want is some sort of an integral. I don't know what the integrand is. We'll deal with that later. But some sort of an integral du dv. Because I want to do an integral on this domain in the uv plane. Right? So this is the situation I face. I got to figure out now, what is it